This is a continuation of the previous video where we did the UART configuration. So here we're gonna write basic functions that we can use to transmit and receive ASCII characters on the UART. So here's what we're gonna do. We're gonna transmit and receive, and we're gonna write simple code that actually will pull the flags. We have transmit and receive flags that could raise interrupts, but we're not gonna do interrupts. We're just gonna stick to simple code. So at the end of the part 1 video, we were looking at the register files, and this is basically the flags and register names we can see from the family users guide. So this is basically a register that contains the flag, and this is the transmit flag. TX is a transmit. This is a transmit flag, and this is the receive flag. These two flags are contained in this register. So this is basically the register containing this bit and this bit. This is the transmit buffer and the receive buffer. Each one are 8-bit. So when I write the code, before I write the code, I'm gonna redefine these two simple names because these are rather hard to type down in my code. So let me redefine this. I'm gonna call it flags. And this is TX flag. This is RX flag. And this is TX buffer. And this is RX buffer, right? That basically you can see they have UCA1, that basically mean USCI, module 1, channel A, etc. But let's make our code nice by just redefining these names. So the first function we're gonna write is used to transmit a character. So let's call it void UART write char. And this is the character we want to transmit over UART. So let's look at a couple things about these flags. So the receive flag is very easy to understand. 0 means no new data, and 1 means new data received. So very easy to understand for the receive. The transmit flag, 0 means 0 means let me think about this for a second. 0 means busy, and 1 means ready to transmit. 1 means ready to transmit. I just want to check these. This could be the vice versa. Let me double check. Okay, so this is correct what I have. 0 means it is currently busy transmitting. 1 means it is ready to transmit. Now, let's look at the transmit buffer. It turns out writing to TX buffer starts the transmission automatically. And immediately TX flag goes to 0. So if you want to transmit something, first you have to make sure it is ready to transmit, and then you just drop the data in TX buffer. This flag will go to 0, transmission begin automatically. We don't have to pull the flag to 0, so that's kind of nice. And similar thing happens here. Reading the receive buffer clears receive flag automatically. Right? So when the new data is received, the flag go to 1. As soon as we read the receive buffer, the hardware knows we grab that data, and the receive buffer clears itself automatically. So we don't have to clear it. So that's actually nice. So accordingly, let's write the function transmit character. What I'm gonna do here first is wait for any ongoing transmission to end. There may not be any transmission, but if there is, we have to wait for it to end. And that means I'm gonna wait as long as it is 0, because 0 means it is busy. So as long as this bit is 0, I'm gonna wait in a loop. You should not be concerned that the loop may take infinitely, because at most we are transmitting 1 byte. I'm assuming no other functions are transmitting in the same code, right? So waiting on the transmission to finish is usually 10 bits times the baud rate, something like that. So it's reasonably a short time to wait on. So let's do this while flags and tx flag is equal to 0. We're gonna wait here, right? So I'm going to the register, look at the flag. If it is 0, means it is busy. We cycle here in the while loop on and on and on. And when it's done transmitting, it becomes ready. This bit goes to 1 and the while loop ends. If there is no transmission, this will only be attempted once and we go to the next line. So now we are ready to transmit. All we have to do is do tx buffer is equal to data, the parameter, and that's it, return. And we know that as soon as we do this, tx starts and tx flag goes to 0. So everything will be done automatically. It's a very simple function. So this will be the function that we can use to transmit UART. You can call this back-to-back. It doesn't matter, because this guy will pace it. It's going to make sure the thing will end, the current transmission will end before a new one starts. But from your main code, you can call this back-to-back. You know, your CPU is faster than UART. You can call this quicker than UART, but we are pacing this guy in here, so this should be no problem. And when we transmit UART, we transmit 8-bit at a time. The transmit buffer is 8-bit. I treat that as ASCII character. You can treat it as a number, but you know 8-bit as a number is only 0 to 255. It's not a big number. So usually I like to interpret as ASCII character. So if you have a big number like integer n equal 1234, this obviously cannot fit on a byte. You cannot transmit. So what you usually end up doing is you parse ASCII of 1, 2, 3, 4, and then you transmit 4 ASCIIs. This is why we think of it as ASCII character, right? If you have a big integer, cannot go in a byte. So you parse it by doing divide by 10 modulo 10. You get ASCII of 1, 2, 3, 4, and then you transmit 4 ASCII. So that's why I think of it as a character rather than just a number. So let's read an ASCII character over UART. UART read character unsigned car star data. So this passed by reference, so we can actually put the data here. You can also do unsigned car here on the return type. Either way is fine. So I'm gonna write this code in very simple way first. Wait for reception while flags and receive flag is equal to 0, wait here, right? So I'm gonna wait in that loop as long as the receive flag is 0, right? Because once new data arrive, receive flag is 1. And once data arrives, we will go beyond that loop. And all I have to do is return Rx buffer. And just reading Rx buffer, the Rx flag clears automatically. Because doing so, we have read the Rx buffer. So this is one way to write this function. The problem with this function is we may end up waiting here indefinitely. We are receiving over UART. We're trying to receive over UART. What if the other guy who's connected to the UART has not sent us anything for like 1 hour? Then my CPU will be waiting here locked for 1 hour. No other part of the code can run. And we're just cycling this. So obviously this could be a problem, unless you ensure the other guy send you like dummy data every second just so we don't block here. But usually that's not the best way to write this. So this is basically a blocking, waits indefinitely until data is received. So that's not really a very good way. So I wouldn't write that, but this is just our baseline. Let's adapt this a little bit. So we're gonna write a non-blocking version, and if no data received, returns null character. Otherwise, return the actual data. So I think that will be nice, right? Because I'm thinking of this as ASCII character. There's the null character, which is ASCII equal to 0. If no data is received, let's return null character. So the code will know no data is received. Otherwise, we return the actual ASCII character. So let's do this here. If no data received, now this is an if statement. So if flags and RF flags is equal to 0, that means no data is received, return 0. The ASCII of null is 0. You can also do return \0 in single quotes, right? Either else, return the actual buffer, and this will clear the flag automatically. So let's look at this function now. This function will return immediately. When it is called, it will return immediately, right? If the flag is 0, it will return null immediately. Otherwise, it will return the actual content of the buffer. So this wouldn't just loop infinitely like this. And that would be more desirable than the first one. One small implication of what we did is we cannot receive data equal to 0, because when we return 0 in here, that means no data has been received. So it's impossible that we receive data equal to 0. How can you differentiate data equals 0 from 0 indicate the null, which means no data is received? But this is okay. If we were treating this as a number, then that would be a problem, because 0 could be an actual number. You cannot use 0 to say, I have not received any data. But since we're using an ASCII character, that's okay. So the assumption here is the other guy will never transmit to me the null character. It will transmit to me A to Z, uppercase, lowercase, 0 to 9, exclamation point, all the stuff you see on the keyboard. So that would work. Otherwise, if you wanna support transmitting the null character, maybe you can return int. And if the int is like -1, that means no data received. This kind of to indicate the status. But I think the way it is now, it should be fine. So that's pretty much is our code. And we can use that in the conjunction to the UART initialize function we wrote in the earlier video to do UART transmission and reception. Just a quick overlook of the next step. If we want to improve this a little bit further, we can use interrupts. So if we use the interrupts, you notice here these flags. Let me just copy this down. This flag is called the transmit flag. In conjunction with this guy, there will be something called interrupt enable, right? Because this is IFG, interrupt flag. And in conjunction, there will be one called interrupt enable. They have the same name, UCTX IFG, UCTX interrupt enable. So I believe that will raise an interrupt when the transmission is complete. So we can start a new transmission. And similarly, here you could have an interrupt when data is received, right? So this is the flag, and you would have receive RXIE. So if you want to use interrupt, you would have to write 1 in here, write 1 in here, and there will be an ISR, which is the actual function. You would have to write the function that responds to these two interrupts. So that's pretty much is, and similar stuff here. It could be the same function. So you can do if else to figure out whether transmit or receive interrupt. So that's kind of how the code will look like. For simple codes and applications, this is okay. But obviously with interrupt, the code will be a bit more efficient because you can put the CPU in low power mode when you use interrupt. But it does actually make the code status a bit, the code state a bit more challenging, because interrupts could occur any moment, and these functions can be called any moment. You cannot clearly visualize the flow of the code. If you write a code without interrupts, you can visualize that. Let me write here. You can visualize that I start in the main here. The main calls function F1, right? Function F1 calls function F2, and function F2 returns, F1 continues, and this returns the main continues, right? And maybe you have a loop to go back up to here. So if you write a code without the interrupt, you can clearly visualize the flow of your code, because you know you are making a call here to F1, you are making a call here to F2. The challenge when you start doing interrupt is your interrupts are here. This is the ISR function. This is another ISR function, interrupt service routine. And this is your main. This is your main here. And you cannot do a flow like this because you don't know when these will be called. These will be called by hardware events. So it does actually make the code a little bit more challenging and could introduce more bugs, but it is certainly worthwhile the effort to use interrupt, because you can activate low power mode. And when you have so many events, you cannot just polling them like this by a predetermined flow. You want these events to present themselves whenever they occur. All right, so that's pretty much it for this video.